Welcome back. Today we're revisiting scaling laws, but with a focus on efficiency, how to get the most out of data, compute, and architectural choices.
We covered basic scaling laws in episode 10. Now we're diving into recent insights and efficiency considerations.
Let's start with data efficiency. We discussed chinchilla scaling, which emphasized training on more tokens.
But are all tokens equally valuable?
No, high quality, diverse data is much more valuable than repetitive or low quality data.
Recent research shows that careful data curation can dramatically improve data efficiency.
You might get better performance training on 100 billion carefully selected tokens than 1 trillion random web tokens.
This has led to increased focus on data quality over quantity.
Techniques like deduplication, quality filtering, and topic diversity balancing matter.
Some researchers use smaller models to select high quality subsets from larger corpora.
The model scores potential training examples, and you train on the highest scoring ones.
This curriculum learning or data pruning can significantly improve efficiency.
Let's talk about compute efficiency.
Different architectural choices have different compute requirements for the same performance.
More efficient attention mechanisms like flash attention reduce the compute needed without changing model quality.
Mixture of experts, which we discussed, gives you more capacity per unit of compute.
Quantization reduces the precision of computations, trading accuracy for speed.
8-bit or even 4-bit inference can run 2 to 4x faster with minimal quality loss.
Mixed precision training uses lower precision for some operations, speeding up training.
These optimizations mean you can train or run larger models on the same hardware budget.
Now, what about architectural efficiency?
Not all parameters contribute equally to model performance.
Research on scaling laws for different architectures shows significant variation.
Some designs achieve better performance per parameter than standard transformers.
For example, models with different layer configurations, normalization schemes, or activation functions can be more efficient.
There's also work on neural architecture search to find optimal designs for given compute budgets.
Let's discuss the relationship between model depth and width.
Depth refers to number of layers, width refers to hidden dimension.
For a given parameter count, should you have many narrow layers or fewer wide layers?
Research suggests that depth is generally more important than width for language models.
Deeper models tend to perform better than wider shallow models with the same parameter count.
But there are diminishing returns to depth. Beyond a certain point, adding layers helps less.
The optimal depth to width ratio depends on the total parameter budget and task.
Another consideration is attention heads versus FFN size.
Most parameters in transformers are in the feed forward layers, not attention.
Some models allocate more parameters to FFN, others to attention.
The FFN size to hidden dimension ratio is typically 4x, but this can be tuned.
Recent models experiment with different ratios to find sweet spots.
Let's talk about sparse models beyond MoE.
Any form of sparsity, activating only part of the model, can improve efficiency.
Magnitude based pruning removes small weights that contribute little.
This can reduce model size significantly with small performance drops.
Structured sparsity removes entire channels, heads, or layers.
This is hardware friendly because it creates actual computational savings, not just theoretical sparsity.
Dynamic sparsity activates different parameters based on the input.
MoE is one form, but there are others like conditional computation.
The model learns to route computation adaptively.
Let's discuss hardware aware efficiency.
Different hardware has different strength. GPUs are great at parallel dense operations.
TPUs are optimized for matrix multiplications at scale.
Some emerging hardware like neuromorphic chips or analog compute could change the efficiency landscape.
Model architectures should be designed with the target hardware in mind.
For example, group query attention is more cache friendly, reducing memory bandwidth.
Flash attention optimizes for GPU memory hierarchies.
These hardware aware designs can give 2 to 5x speedups with no model changes.
Now, let's revisit data compute scaling trade-offs.
The original scaling laws suggested a particular balance between model size and data.
Chinchilla revised this toward more data for a given compute budget.
But the optimal balance might differ based on deployment constraints.
If you'll run the model billions of times, you want to minimize inference cost, so train longer on a smaller model.
If you'll only run it occasionally, maximize quality for given training budget, which might mean a larger undertrained model.
There's no single optimal point, it depends on your use case.
Let's talk about multi-epoch training.
Chinchilla optimal training typically uses data once or less.
But if you're limited by data availability, you might train for multiple epochs.
Each additional epoch gives smaller improvements, following a scaling law of its own.
But careful scheduling and regularization can make multi-epoch training effective.
Some domains with limited data, like specialized medical or legal text, benefit from multi epoch training.
Now, what about scaling for specific capabilities?
Different capabilities might have different scaling laws.
Factual recall might scale differently than reasoning or creativity.
Some research shows that certain tasks require threshold model sizes, they don't scale smoothly.
These are the emergent abilities we mentioned before.
Understanding capability specific scaling helps prioritize where to invest compute.
Let's discuss inference efficiency separately from training efficiency.
Training is a one time cost, inference happens repeatedly.
For deployed models, inference efficiency often matters more than training efficiency.
Techniques like KV cache, speculative decoding, and quantization are primarily about inference.
Model distillation is also mostly about creating efficient inference models.
The scaling law for inference is about throughput and latency versus quality.
How many queries can you handle per second and at what latency for a given quality level?
Batching strategies, caching, and parallelization all affect this scaling.
What about scaling for different modalities?
Vision transformers have different scaling properties than language models.
Images have more inherent structure and locality than text.
Video adds temporal dimension, which scales differently.
Multimodal models combine these scaling behaviors.
Understanding modality specific scaling helps design efficient multimodal systems.
Let's talk about the limits of scaling.
Are there hard limits to how far scaling can take us?
Some researchers argue we're approaching data limits. We've used most of the internet text.
Compute costs are also a concern. Training the largest models requires tens of millions of dollars.
Energy consumption is significant and raises sustainability questions.
And there might be theoretical limits to what pure scaling can achieve.
Some capabilities might require algorithmic innovations, not just more scale.
This is why efficiency improvements are so important.
If we can get 10x better efficiency, that's equivalent to 10x more compute for scaling.
Let's discuss post training scaling.
Besides pre training, there's scaling in fine tuning, RLHF, and instruction tuning.
More post training compute and data can significantly improve deployed model quality.
The scaling laws for post training are different from pre training.
You typically see faster improvements per additional sample, but from a smaller absolute baseline.
Investing in high quality post training data can be very cost effective.
So, to recap, data efficiency improves with curation and quality filtering. Compute efficiency comes from better algorithms and hardware awareness. Architectural choices significantly affect parameter efficiency. The optimal balance between model size, data, and compute depends on deployment needs. Sparse and quantized models offer efficiency gains, and there are emerging limits to pure scaling, making efficiency crucial.
Next episode, we're exploring infrastructure for training LLMs, the systems and engineering that make large scale training possible.
Thanks for listening.
Until next time, keep learning and stay curious about AI.